Hello, we are Team 17 of Embedded System Design, and for our project we designed a value-seeking robot. I am Arman Adibi.
I am Hao Kang.
I am Bryn Onweller.
And I'm Michael Severance.
On one side of our field is the block pool, which contains 7 colored blocks. Each color has a point value associated with it. Red blocks are worth 3 points, green blocks are worth 2 points, and blue blocks are worth 1 point. The main goal of our robot is to obtain the 3 highest valued blocks from the pool. Our robot starts on the opposite side of the field from the block pool. First, it must drive to the blocks and identify the colors of each block. Using this information, the rover is able to determine the positions of the 3 highest valued blocks. It then picks up these blocks one at a time and moves them to the other side of the field and drops them in the designated drop-off zone. Once the robot has collected all 3 blocks, it drives to the center of the field and draws the total point value of all the blocks it has collected on the ground.
Before beginning our design, we came up with a list of constraints. Some given restraints are that our field could not have more than 25% of the perimeter be a barrier, and our robot was not allowed to follow lines on the ground. Of the hardware provided to us, we had to use PIC32 boards that each ran independently of one another, and they had to communicate only through a server. Based on our design, we decided that for our project to be successful, the batteries on the robot needed to last for the entirety of the run, and that the robot could not damage any of the components in our field.
This is our robot, Roger. He has an arm in the front for picking up objects, and on the side, we mounted a pixie cam for scanning the 7 blocks. Under the arm, we have another pixie cam for beacons and a time-of-flight sensor for range finding. We also have a pin taped to a servo to draw the point value at the end. On the back, we have the 2 onboard microcontrollers for logic. We also have an off-board microcontroller for sending commands to Roger, and a Raspberry Pi as the server for wireless communication.
The Zumo rover base provided contains motors controlled via pulse width modulation. The duty cycle of this PWM signal controls the motor speeds, so a higher duty cycle will result in a faster motor speed. In addition to the motors, encoders were installed on the base, and they can be used to keep track of the rotation of the motors. So as the motors rotate, the encoders will send square wave pulses when the motor shaft passes a certain position. These pulses can be used to control an external clock, in our case, which has a period of 30 pulses, so every 30 encoder pulses received by the clock will equate to a single encoder tick in the motor control algorithm. A proportional integral derivative control, or PID for short, was implemented to utilize the encoder values in order to make more accurate and consistent turns and for driving accurate and consistent distances. The way this PID control works is by calculating the error from its destination, which is essentially where it wants to be, that's provided by an input, minus where it currently is, which is provided by the encoder values. Using that error value, the speed of the motors through PWM is set to be proportional to how far off it is from its destination. So when the rover is far away from where it wants to be, it'll drive faster and it'll slow down as it approaches its target. The PID control is also self-correcting, since if the error will become negative at any point, the motors will reverse and undo anything that they overdid. And the error value for this PID algorithm is recalculated every 50 milliseconds with new encoder values to ensure precise operation. And these distances for turning and driving are all determined experimentally with a precision of 1/2 inch for driving and 6 degrees for turning.
Both the arm and the pen components were controlled using a pulse width modulation signal through servo motors. The PWM signal will set each servo to a certain angle that will allow the arm or the pen to be in the correct position to pick up for each of its performed tasks. The arm performed one of 2 main tasks: pick up the block or drop the block, based on the command received by the compute pick. Once it completes its task, it returns to the idle state to allow for driving without blocking either the time of flight sensor or the pixie cam. The pen remains in the pen up state until the robot is ready to draw the calculated value in the center. Because the value is drawn as a 7-segment display, the pen remains in the down state while the robot drives forward and is up while the robot positions itself to draw the next line segment.
For the color sensor, we use the pixie cam. It is a camera with an onboard computation chip, so our microcontroller don't have to analyze the video. Since it is a camera, it is able to detect color objects far away, which fits our needs. The communication protocol that we used was UART. Below is a software called Piximon, which allows us to see what the pixie-cam sees. On the right side is the configurable settings included with Piximon. This software was useful because it allowed us to tune the object detection live. For each of the color signatures, we are able to change the detection sensitivity so it can accurately find objects in whatever environment it's in. These 2 pictures show what the pixie-cam sees once the specific colors have been taught and tuned. The left is one of our beacons, and on the right are the objects the robot will pick up. The pixie-cam can be very accurate if the settings are tuned properly. The pixie-cam communicates using data packets. To initiate a request, you must send it a specific bytes and wait for its response. On the left shows the general format for all the requests, and on the right it shows the specific bytes needed to get block information from the pixie-cam. Once the microcontroller sends the request bytes, the pixie-cam will respond with the bytes below. The key information we looked for was the signature and x-coordinate for each block.
My main contribution was the compute module. This module functioned as the robot's brain and was responsible for the overall mission algorithms. To accomplish this, I need to design a procedure to send commands and read data from the other components. When I want to issue a command to a component, I post the desired command to the server along with the unique command number. When the target component receives a command, they post the command number I sent to their own endpoint. By checking whether the command number on their endpoint is equal to the one that I just posted, I can tell when a specific command was received. Some components, such as the motor and the arms, require some time to actually execute the command after they receive them. To account for this, each component also updates their state on the server to represent the current command they are executing, or idle if they are not working on a command. By checking the state of the component, I am able to tell when they have completed a command and are ready to accept a new one. Using this procedure, I was able to implement various control algorithms, and I'm going to talk about two of the most important ones listed below. First is the beacon alignment algorithm. Using the motor encoders to drive straight and make precise turns works out alright, but unfortunately is not quite accurate enough for our application alone. So we had to come up with an external way to correct for motor inaccuracy and drift. We chose to use beacons placed at strategic locations on the field to help us account for drift and make important turns. The PixieCam is able to detect these beacons and sends me the X and Y pixel coordinates of the object it's detected. Using the X coordinate, I am able to rotate the rover either left or right and try to center the coordinate in frame. The next algorithm I implemented was driving straight to a target distance. This algorithm allows us to quickly and precisely navigate to a desired distance away from the beacon. For this algorithm, I only allowed the robot to move forward a maximum of 10 inches at a time before attempting to recenter with the beacon. This ensures that the rover does not drift too much while driving. Additionally, when the rover is within 2 inches of the desired destination, I only allow it to drive 1 inch at a time. This increases the accuracy further by forcing the rover to recenter more often.
In terms of the reliability of our rover, our design is fairly reliable, so it is capable of running for long periods of times, with the only issues really being the Wi-Fi connectivity. So if the Wi-Fi module disconnects on the compute microcontroller, then we have to restart the entire mission. However, if a Wi-Fi module disconnects on one of the onboard microcontrollers, then all we need to do is simply reset that board, and then we can continue the mission where we left off. Additionally, the PixieCams work much better in brighter environments, but they can still function pretty well in most lighting conditions because of the camera brightness settings. So overall, we have about an 80% success rate in our runs, and this is also due to issues with the arm movement because it would knock over blocks if the distance between the rover and the block is not correct.
We designed our system to be fairly robust overall. Our wireless communication was designed so that hardware components continually post their state and command number every 200 milliseconds. This way, if any message fails to reach the server for some reason, it'll be updated the next time we post. To account for some interference in our readings, we return the median of 5 values each time we pull the time of flight sensor. This way, a single bad value will not affect our final result. We corrected for inaccuracies in the motors by combining other sensors. For example, we accounted for motors moving the wrong distance by using the time of flight sensor, and we accounted for the rotation inaccuracy using beacons in a PixieCam.